So much for everyone joining us in class today with Matt. So a little introduction about Matt. We're so lucky to have Matthew Muller here with us this week. A little bit about him. Matt is a designer, builder, whose work balances adaptation, function, and lightness, moving between object and architectural scales. His intuitive design process is grounded in material experimentation. After obtaining a BFA in furniture design from RISD, Rhode Island School of Design, Muller co-founded Newhouse, a Providence-based studio that has spent now a decade honing the craft of inflatable architecture. Building on the legacies of Buckminster Fuller, Frei Otto, Newhouse's work has been exhibited across the US and Europe, and now Bloomington, Indiana, 2 days in a row. Newhouse is an art and design studio that specializes in playful transformations of public space. Their immersive sculptures and environments guide visitors into the universe of their senses and the joys of shared experience. Inspired by physics, biology, and craft, their studio's work incorporates the lessons of nature in both form and function. Please join me in welcoming to the Eskenazi School, Matthew Muller of Newhouse.
Thanks so much for having me. Thanks for the introduction, Max. We had such a great time in the classes today, building the large inflatable donut. And I'm excited to have the opportunity to share more about our studio's practice, how we operate, and how we come up with our ideas and bring them to life. So because we're a collective, there's 6 of us total now. There are 3 founders, myself, August Larica, Levi Vidal, and then now we've grown to David Guzmanov, Hannah Dunnigan, and Kipper Rhinesmith. If any one of us gave this talk, it would be different. It would have its own flavor. We're all kind of like equal at the design table, but we have our own specialties. I kind of focus on more of the fabrication, material, execution side of things, so you're getting that version of it today. So that said, I like to kind of start with the key principle that makes inflatables such a potent medium if you're interested in large-scale fabrication. I'm sure there's a lot of architects and designers here that are familiar with these 2 primary forces of tension and compression. And we're trying to make something really large that is as lightweight as possible. It's often advantageous to identify when those 2 forces are happening and use a material that is better suited for one or the other. Compression is usually dealt with concrete, steel, wood, these like heavier materials, while tension you can deal with thin cables, fabric, rope, etc. So the huge advantage of inflatables is that the heavy compressive material we don't need at all. We just borrow it from the environment wherever we happen to set it up. It's just air. And the fabric that we are sewing together or welding takes the tensile load. Now, I also like to give a little bit of just a real brief history of inflatables, at least through the lens of a material challenge. So for over 5,000 years, humans have been using animal skins to make rafts called keliks. That's what they're called in ancient Assyria and ancient Egypt. And they've shown up in different indigenous cultures in various forms all around the world as well. But a kelik is you take any kind of animal skin, skin the animal with as few cuts as possible, ideally just on the limbs, stitch it back together and seal the openings with animal fat. And they could actually make fully airtight bladders this way. Like this is, as someone that has like all these fancy materials and tools to do this now, I have so much respect for the people that did this, and there still are actually a few in Southwest Asia that still do this. But it's an incredible kind of like human achievement. And there's actually in ancient Egypt, there's documentations of rafts that were made of over 1,000 of these skins. And if afterwards, if of my opinions on how the pyramids were built with these, so we can get into that. But so that, for about 5,000 years, that's pretty much what inflatables were. They didn't change much until the Industrial Revolution. We started processing natural rubber, developed vulcanization, and that process was still really material intensive. So there's like an explosion in the 19th century of these amazing like object scale inflatables. And this is one of my favorite, the Halkett boat. This was a boat made for exploring the Arctic. So you wear it as a cloak when you're walking on land, and then you get to an impassable part of water, and you take it off and you inflate it, and you open your umbrella, let the wind take you across, get back on land, deflate it, put it back on, and keep going. And they actually use this. This is actually used. And for about 100 years, the rubber was kind of used in these small, amazing things, like tires, or the kind of famous industrialization of it. And then when we get to World War II, Walter Bird is credited with bringing it to architectural scale. So these are radar domes. An amazing thing about inflatables is that there's very little wall thickness. So if you're trying to figure out a way to shelter a giant radar dish that needs to be able to spin freely, fully around, and be as invisible to radar, like the radio waves, as possible, this is a pretty good solution. There's a big spinning dish in there, and this kind of protects it from the elements. And this is really significant because a lot of architects and artists kind of saw these domes and were like, this is an entirely new way of building space. And it really unleashed the imagination of a lot of the kind of architects, and especially like the hippie movement in the 70s. So now I'll touch on a couple of those people that particularly inspired our studio. Frei Otto, kind of like the father of like material computation. If anyone that uses like Grasshopper or any of these parametric modeling programs now, if you're not familiar with Frei Otto, I highly recommend looking into him. Particularly there's a book, Thinking by Modeling, showing the model making process. But this idea of material computation, where you set up these parameters using wire and rope, and then you use the properties of various materials, such as soap film or latex, to solve really complex structural issues. So in the bottom left here, you'll see this kind of cooling tower shape. That is a metal wire frame at the top and the bottom, and then by dipping that in soap film, the soap film reveals the minimum amount of surface area to connect those two boundaries. Right? So we can do that now on the computer, but he would actually make these physical models and then make these amazing intricate probes to like measure them exactly, translate them into drawings, and then make pavilions out of them. He didn't actually really make any inflatables, and that again is a materials issue. There weren't materials that were flame retardant or had the tensile strength at the time, but he left behind an amazing record of exploration in pneumatic forms that we benefited greatly from. Actually, like on the material, the Munich Olympic Stadium there in the middle is this kind of like tensile structure that was derived with soap film, but because there were no textiles that could achieve that, it's actually built out of metal cables with glass panels mounted to it. So it's just like a really intense way to recreate this fabric-like structure, but it was the only way to be able to execute that. Then we could getting into the kind of utopian hippie architect movement. This is Utopia. They were a French collective that, as far as I know, didn't really build anything, but they illustrated these just insane visions of like an inflatable future. This movement was in large part a reaction to the brutalist architecture at the time, trying to center architecture more on the human body, on the human experience, and ephemerality inherent in that. Whereas brutalism had this kind of like permanence and the power of the state and all this. House Rucker is a big inspiration to us. They were an Austrian collective, and they had similar critiques of like capitalism and urban living, but they also actually built stuff. And so the house, and New House, actually comes from them, not Bauhaus. And when we were first developing our practice, we really appreciated their conceptual rigor as well as their commitment to executing things at a very high degree. In our studio, August Lerica and I, who kind of started out as students, we will say furniture design, and the thing that really kicked us off into that, into inflatables. We were both like studying woodworking and all this. Then a friend of ours gave us the inflatable cookbook. I had made like 1 or 2 inflatables as a freshman, and a friend came across this document and sent it to me. And Augie and I were both interested in lightweight structures, and he wanted to make an airship for his thesis, and I wanted to make this like fully foam, soft space. But we ended up following their tutorials and making a 40-foot dome out of like $100 worth of plastic, and doing like a student-run multimedia exhibit inside it. And that kind of lit the spark in us. We're like, this is crazy. It was such a potent experience. It looked something like that, you see on the bottom left, but a little rounder. And that's what kind of kick-started our thesis. And we're like, we both dropped what we were thinking of doing individually, and we're like, well, let's convince our department to let us do a joint thesis exploring the craft of inflatables in the way that the department had taught us to treat like furniture. So focused on craft, focused on human interaction, and also then what that craft kind of allows us to do. And so that's Ant Farm. And then fast forwarding 40, 50 years, materials have solved all the problems. And the synthetic textile world is great. It can solve any material problem you want. And for that reason, well, I mean, a lot of it is actually thanks to like space exploration, NASA stuff, all the technical materials we have now have kind of come from that. These are just 2 kind of examples. Like the benefits you get from pneumatics, like structurally, efficiency-wise, just multiply tenfold when you get into space. When you don't have to worry about gravity and it's all pressure systems. But yeah, here on the right is the NASA Echo 1. That thing is just meant to reflect radar signals, so it goes up into the upper atmosphere. So satellite can hit that with radar, any kind of radio wave, and it will bounce down to the Earth, so you can kind of like relay. And then these are inflatable space station modules, one of which is on the space station right now. And they're actually much more resilient than traditional rigid hulls because meteorites will bounce off of them rather than dent them. But yeah, a lot of times people think inflatables are really delicate, but in a lot of situations they end up being much more resilient depending on what you're looking for. Okay, so now you have some of the context of how we think about making inflatables. Now imagine it's 2014. You just graduated, you're living in a warehouse with 5 friends, and some students are putting on a design conference, and they want you to make a lounge. An inflatable lounge, they don't have any other requirements, they have $2,000, and you're like, oh my God, this is the most money I've ever heard of. At this time, we were having a lot of fun playing with soap film, and blowing soap bubbles, and the way that we were learning from Friado. And we kept coming to, like when you're doing that, you just keep coming into this 3 soap bubble intersection. It's really stable and it just pops up all the time by accident. We really like that form. And we're like, okay, let's make that form. It's really stable, it looks good, but what color do we make it? And we're a collective, so we can't just kind of go with like, oh, I like yellow, Augie likes green, Levi might like blue. We can't just pick an arbitrary color. We didn't want to make it white, that would be boring. And so we were tortured for a while. And then at one point, we looking at the plan view of it, we realized this is like a Venn diagram. This looks like the additive color diagram. So what if we just make each low one of the primary colors? So like if you look at each pixel on this projector, each pixel on your phone, they're going to be red, blue, and green. And by adding together different combinations of those colors, you can make any color in the visible spectrum. We actually have 3 cones that roughly align with those colors. That's what these humps are. Each one is actual type of cell in your eyeball. And so yeah, so we went with that idea. We were like, will it actually project a rainbow onto the ground? That was our idea. And we made a small scale mock-up, and it worked on the small scale. And eventually we were like, okay, can we actually execute this on a large scale? And we just took the leap of faith and did it. And it worked. You can see, if you look at the bottom there, you see yellow in between the green and the red. You'll see magenta here, cyan. And it, along with, just the ability to walk into one of the colors and like fully saturate your cones with a single color and getting the after image. So we had a lot of fun playing with that. But we found that we would have to tell people to look at the ground. Another amazing thing about this is like if you look at the wrinkles, you can see there's variation. Every time you would step on the white ground, all the wrinkles around your foot would be just every color in the rainbow. So it's this kind of always changing iridescent kind of quality to it. But people, when they walk into something like this, they go like this, they look up. And so we have to keep telling them. So that, it's very unsatisfying to have to tell people to look at the thing that's interesting on your piece. Here's some other views of it. It's like if you crop, right? So it's like if you crop out the really saturated colors, you can see all these subtle colors better. But so we thought, how do we present that effect? If people don't like looking down, they want to look up. So we wanted to create that effect in a way that was more vertical. And at the same time, we also wanted to try a new kind of inflatable structure, or new to us. So this is what we would call an air inflated structure, or a single membrane, where you're going inside the pressurized space. But we really wanted to make a double membrane, more like a quilt, and you don't go inside the pressurized space. And we thought, what if we make a quilt that is just a bunch of cells? So rather than one big pixel, it's a whole bunch of pixels. And this was a bit of a disaster because the material didn't have the right coating on it, so it wasn't airtight. It was really soft. This is for a gallery show at Pratt that, again, didn't have very much money, but they didn't really care what we made, which was a great opportunity for us to keep exploring this thing we're interested in. And it worked out. We had lots of little rainbows. But we don't want to just hang a thing in a building. We like to make spaces. So we were like, okay, next chance we get to make a pavilion, we're going to turn this into a structure. And that's what we call Kitic Prism number 2. We just kind of call it Kitic Prism. So we got the right material, got airtight stuff. We make it firm. And it's this kind of barrel shape. And it's a complicated geometry, how cubes become hexagons. I won't get into the geometry nerdiness of it. But as the sunlight hits the piece from different angles, we get a rainbow inside that varies in intensity on different colors. So right now the sun is predominantly kind of hitting the red, but throughout the day as the sun moves, it will become a little more green, a little more purple. And that it was a really big success. Most people when they interact with something like this, they think there's LEDs in it, they think it's some kind of digital projection, but it's fully analog. It's just a filter for natural light. That's why we call it prism. And then also as you walk around it from the outside, you get this kind of feature where some angles you'll fully get one color and some you'll get the other. So another lineage that we've been exploring is optics. So Augie had made like a pinhole camera and I think also like a camera obscura that was meant for tracing when he was a student. And we had talked a bunch about making an inflatable one. And we met some photographers who, at RISD, who would would set up a plywood camera obscura for this festival every year. And it was really difficult to assemble, and we told them, we need to make you an inflatable one. Not only will it be much easier to set up, but the kind of analog to an eyeball, this kind of like round dome thing, it would just be a kind of like a much more kind of like complete version of it. So anyone not familiar with the camera obscura, it's the most kind of primitive camera. It's what any camera uses that principle. It's a dark box with a single hole in it. Our eyes use the exact same principle. And the image coming through gets flipped upside down. This diagram kind of shows why that is. You just like have a laser pointing. You can see if it's up high, it's going to have to go down to get through the hole. And so for this, the inflatable had to be totally opaque. When we actually first inflated it, we didn't cover the stitches, so it didn't work at all. It was beautiful. You could see like this grid of stitches everywhere, but we had to figure out how to seal them up and make them dark afterwards. But yeah, here it is. It works amazingly. They have little apertures that we can adjust the opening with, so when you walk in, we'll have it open a lot. So it'll be a pretty blurry, bright image, and then the longer you're in there, the more you can close it, and the image gets more and more crisp as your eyes adjust. Now, we did this, we were like, okay, that's cool, but many people have made camera obscuras. What if we do to it what we did to the fabric prism and multiply it times 109? And that's what we call the compound camera. So this is what was set up in the Mies van der Rohe building yesterday. So this is, again, we're going from a single membrane to a double membrane, and kind of taking that whole structure and just making it one of the cells. And when those little black dots you see there are lenses. And when you walk inside, you see a live, totally analog projected image of the outside world all around you. Each cell is flipped upside down and left and right, so it's incredibly disorienting. But yeah, this image is actually flipped so that it makes a little more sense. You can see my home truck there. But yeah, so this effect, most people when they go inside it, totally convinced there's like a million cameras and projectors, which would be way too hard. We would not have been able to do that. But we just kind of meticulously tested out the right lens size. The outside fabric is opaque. The inside fabric is translucent, kind of like tracing paper, but it's like a nylon that's strong. And there's like these internal walls that are light blocking, so that each cell is its own crisp image. And it kind of gives you this fly's eye experience. And yeah, so we kind of like, we pick these different phenomena and we just kind of work our way through them. The like ideas are usually pretty basic, and we just kind of try to walk through them one step at a time. But yeah, so this, we were given a chance to do a gallery show. So most of our work is outdoor public art, which kind of comes with a lot of limitations on like what you can do. Like, you know, the environment is much more harsh, dealing with rain and wind, and people are kind of more intense. When they see an inflatable, they just want to like run into it. So doing a gallery show was like, oh, it's like totally have to rewire how we're thinking about our work. And we were fascinated with this, the feeling of being inside an inflatable. There's something like completely uncozy about it. Like when you're inside the pressurized space, like in this room right now, we're kind of like feeling the weight of the ceiling in a way. Like if you go into a cathedral, they try to eliminate that feeling and add that like uplifting feeling, that feeling of like anti-gravity. Inflatables have that as a default. And we wanted to explore what is it that is causing them. So we thought, let's make a sphere that people can go inside, and then let's make the opposite of a sphere. And so it's just about the curvature of the surface that you're in. And the sphere is pressurized, positive pressure. This is actually a vacuum. It's a negative pressure space. So we had to make a wooden frame so that it wouldn't just implode on itself. And we put them in a room together, and you could go inside one and then the other. And it was just to kind of show people like, what was that feeling? So this is actually like when you pack spheres together, like if you see oranges at the grocery store. Sphere packing, there's a whole science behind it. There's a lot of different ways to pack spheres together, surprisingly. But this is this is our favorite type of sphere packing. If you took out the negative space from that, this was exactly this. And this is what they're like inside. So the vacuum looks really scary and pointy on the outside, but when you go inside, it's like you're between these spheres. You just see little sections of them. And it did feel very cozy, really comfortable. The sound was really dampening. It had this incredibly anechoic effect. And the sphere is just terrible. Being inside the center of a white sphere like that is like some kind of torture. If you do it long enough, your voice is amplified right in your own ears. So it sounds like you're yelling into your ears even when you're talking normally. And you just feel exposed. It's a kind of weird feeling, but that's what this piece was looking at. We're also interested in how planar the spaces are. We got a flat plane here, then we have stairs, which are like a teleporter to another flat plane. And these spaces that, a lot of us were drawn to spaces that broke that kind of planar space quality. So we had an opportunity to do an installation at Burning Man where you don't really have to worry about liability of people falling off high things. So that was our chance to do a giant planar structure and explore this kind of trying to make a space that people could interact with each other three-dimensionally. Kind of getting back to our monkey roots. This is fancy ways of saying we want to make a playground. And that's what this is. It's called Pliescape. This is before we had the machine to make airtight stuff, or one of the machines. So these are actually stock available ship vendors. So if you have a $1 million yacht and you don't want it to crash into a dock, you would buy a couple of these and have them hanging off your boat. We bought them for like $1,000 each. And they can hold 50,000 pounds of force. So a really great structural column. And they're nice and soft too. So if we put rigid columns in this, it would be something you could hurt yourself on and play. And then we worked with a net company that helped fabricate the net components. And yeah, it ended up really offering some interesting interactions through space. They also ended up having amazing acoustic properties, a lot of drum circling happening by hitting the big columns. So another idea that we're absolutely cursed with, which is on pause now for how many times it has failed, but I will talk you through that failure, is pneumatic masonry. So we do a Design Science Symposium at RISD. It's a bunch of geometry nerd convention, and they had a little bit of a budget for us to make a new version of it, and we focused on the individual ball. Now it's totally separate, and it has this harness on it that's based on the geometry of a carbon atom. So it's actually these little red clips, if you can see them, they have 4 connections. And the harness around the beach ball has clips in the right places that carbon atoms will join together. So the beach balls are actually kind of the negative space between the atoms, and the little red clips would be the atoms in this case. But using that, we could then make these, they're discovering all these nanostructures with carbon right now that they can assemble. And we're like, oh, we can make those at furniture scale. It was really fun to do, but the clips were destroying our hands. So we don't use it that often. We still have it, but we do come back to that later. Then we get our own hot air welder. So now we can make airtight stuff. This is a machine that would be used to make a dinghy, like an inflatable boat, a Zodiac, that kind of thing. So really heavy duty. And then we got the comments we can do pneumatic masonry now. We can make our own cells. We can make them really high pressure so that when it gets cold, the shrinkage isn't as much of a problem. And we can put tie points directly on the cells. So we don't have that harness, so the balls don't slip out of the harness. I didn't tell you about that. Slip out of the harness. And we solved a bunch of those problems, but then we created new problems because then it was really heavy and it didn't like to do clear spans the same way pneumatic masonry did. So, shelved again. So this is actually one of our most recent pieces. This is in the lineage of pneumatic masonry, but it is really similar to that smaller scale one, where we wanted a playful building block. So this is for the Perot Museum of Natural Sciences in Texas. It's still up, and the exhibit, they purchased it. The exhibit's open at least through June if you find yourself in the area. And I'm sure they'll put it up again later. But we made hundreds of these magnetic modules. So, I mean, there are big illuminated light things. Those actually aren't what I'm talking about here. But these are radio frequency welded modules with magnets on the ends. The red cap, or the yellow cap has like the north pole of a magnet, the blue cap has the south. Maybe it's vice versa, but you can put blue to red, and you can build with the same kind of carbon structure. And because the joints are flexible, we kind of gave them this like hourglass shape so that they could bend and adapt to different forms, which is actually kind of what happens on a molecular scale. But yeah, you could see it. It's a lot of fun. The walls in the room are like stainless steel mirrors, so you can snap it to the walls too. In the lineage of play and scale, we really like a really powerful thing about inflatables is allowing people to have like agency over space, and especially moving really large objects, particularly kids. It's just so empowering to like actually be able to change space. You know, it's like everything's kind of set for them. But adults love it too. They lose their minds as well. But so this is a ongoing project we call Monoliths. This is the latest version we just completed this winter, or actually last fall. We just exhibited for the first time this winter. And yeah, they're just different primitive shapes that we're obsessed with. This is like an octahedral jack, a sphere. In the background, the orange thing you can see is called an oloid. It's like 2 intersecting rings. Tetrahedral jack, and they have LEDs in them. We have to figure out how to keep batteries inside them in a way that wasn't like a hard thing that would hit you when it's rolling around. That's what the little dark hexagon circle thing is. But yeah, so these are kind of like an ongoing development that we're working on. Yeah, and that's what I have today. So our studio we're practice based. We're like, it really is, each project, what we learn fabricating it, installing it, observing how people interact with it, leads into the next idea. It's a lot of times when people see our work, it's just this kind of like, not really understanding of where it comes from. It looks kind of alien. But I don't know, I hope today I've kind of demystified it and kind of showed you the iterative process and just commitment to what pneumatic forms kind of want to be and following that, and also what people want to do with them, including ourselves. Our studio is usually a mess like this, full of different things plated. We also make our design through small models all the time in the lineage of Fry Auto. A lot of times people will see these wireframe lattices in our studio, and they'll be like, "What is that? Those are not inflatable. Why do you have all of these?" But we actually kind of view them as wireframes of inflatables. So we make these 3D lattice structures we're totally obsessed with. No, I didn't show you any of this. But they're really difficult to both comprehend and looking on them on a computer screen. We're modeling them in Rhino. So we have to make physical models to kind of understand the different ways that they interact with each other and come together. And on that note, I'm going to mute myself for a second. take questions in a minute. I don't know if the fan will be too loud and turn off if it is. I've mentioned the carbon atom a bunch of times. We are obsessed with the way that it arranges and the geometries it allows. This is called a diamond lattice because this is the molecular structure of a diamond. The carbon makes 4 bonds. They like to spread out evenly in all directions. And this is how they arrange when there are no impurities in it. Yeah, you can see each node has 4 bonds. Can we put some color on it? Oh, okay, the color. I was trying to project the color onto the lattice. Okay. Yeah. Yeah, if you have any questions.
Just like wrapping up, I'm kind of curious if you have any advice for comprehensive designers or artists or designers who are trying to start something up out of undergrad. I know it was kind of a scrappy thing. It's never the same way, but I'm just curious if you have any advice for.
Oh, yeah. We hacked our way through the first couple of years, but it really, like, collaboration it's really difficult to learn in, like, art school what you need to operate as a professional creative person, because you both want to find your own creative voice, but then you really need to learn how you work on a team. And how much, like, you want to, like, give all of your creative energy to a collaboration, but then you also need to have a little bit of space that when there's a fundamental disagreement, it's not like an existential crisis, and you have, like, some kind of barrier to navigate and figure out how to, what you're good at, what you're bad at, find the people that are interested in the same kind of questions, but have totally different ways of solving them, and work with those people. Yeah, I mean, like, the single artist as genius thing is a scam. Don't fall for that. Find friends that are productive and into the same thing. That's all I have to say on that.
Great.
Give Matt one more round of applause.
Yeah.